Hi, everyone. I am very grateful for the opportunity to speak in this beautiful place. I am a PhD student in ARI at the University of Heidelberg. And today I would like to tell you about the results of my internship at the Lawrence Livermore National Laboratory that focused on providing tools that can help optimize the microlensing community's black hole yield. And thank you to the amazing Livermore and Berkeley Black Hole Dark Matter collaboration. So why do we even need those tools? So you'll see in a moment, the sky is ever changing. We have this variety of twinkling stars, where each twinkling star is microlensing event. And this is just 300 events from Gaia. With Roman and Ruben, we will have tens of thousands of events. So our stream of data will be ever increasing, and it's reaching a point where it's impossible to do it on an event by event basis. So we can't just classify it by human inspection or do dedicated modeling for every event. There is definitely a need for automatic tools for microlensing studies. Astrometric follow-up or any positional measurements are still required to confirm a black hole. And they are still very expensive, so we need to schedule observations on world-class observatories like HST, JWST, or VLTI. Time is very expensive and oversubscribed, and in the case of classical astrometry, you need to have baselines of years. So there's definitely a need to select the very best events where we know that there's a high probability that it can be black holes. And even with Roman, for most events and for most of the sky as well, we will have only photometric measurements. And there's a wealth of black holes hiding in these photometric measurements. And if we do all sky observations and all sky black hole detections, that can also tell us something about the population, the galactic structure. So last but not least, and definitely not least, we are motivated by this recent discovery of the first isolated stellar mass black hole that tells us it is possible, and we can start filling the stellar graveyard that is currently dominated by binary events with singles and see if we can solve the mysteries in the mass distribution and how many of the mass gaps are just observational biases and so on. So there's definitely a need for optimizing our black hole yield. So now I will move on to our classifier. And the concept is very simple. So we want to get the probability of a lens belonging to a given class, given the data and a certain galactic model. So of course we set out from the Bayes theorem and we see how we can obtain all of the ingredients. So moving on to a graphical representation of this. I just meant to mention as well that in this classification, we do not need to consider the detection efficiency of the survey, and if you need a derivation of this point, you can see Scott Perkins' recent paper. So yeah, let's move on to this image. So the blue part, that's the samples, is also represented in blue here, and we do not indicate any good or proper method of obtaining these samples because that will depend on the science case and the resources. In this study, we used samples from a Golovich et al. Study, which includes very complex effects like variability in the baseline. And this is represented by this blue distribution here. And the candy-colored solid distributions are populations simulated by Popsicle, so our trusted lensing event simulation software. And this is where it's really amazing to work on these problems at a facility like Livermore, because those simulations take tens of node days per run. So it's very good to have access to this fast compute. So conceptually, we just look at how similar our blob of the posterior samples is to any of the simulated distributions, and then we correct it for the priors used. And we can use, in principle, any parameters, but we use log TE and log pi E because A, it's easy to constrain them from a light curve, and also B, as you can see here, black holes are really nicely separated in this space, which makes it optimal to classify them this way. And let's explore this space a little bit. So this figure is from our paper that has just been accepted this month, and all figures will be from the paper unless indicated otherwise. It's already on archive if you would like to see it. And this figure in particular, we want to explore the space by looking at every grid point and saying, if the parameters of an event were fixed at this grid point, what would be the probability of being classified as each of the events? And you can see two things from here. So the first thing is that we can make high confidence classifications of stars and black holes. If your science case is, for example, neutron stars, it's not really possible because they are nested in a far more numerous star distribution. So you would need additional information such as astrometry. But for black holes, this is a very nice space and a very nice use case. And the second thing you might have noticed is that we have this weird black blob in here that doesn't really look like anything. And actually, it is a crucial part of our classifier. So, of course, no classifier is perfect. And in this framework in particular, there are two reasons we can have imperfections. So we can have some missing physics. Maybe there is an empty space somewhere in this plot where we don't have simulation samples, but there is some missing population, like primordial black holes, for example. But even if our galactic model was perfect, we can still have an effect from just sampling on the edges of this distribution, where classification is just dominated by numerical noise, and it causes those weird artifacts that you can see here on the left side. So we created this non-class that basically delineates the regions where we have no simulation support. So our classifier can say, I am 10, 20, 50% are certain about this classification because I have samples in a region where the simulation doesn't know anything. And with all the ingredients already here, we can start applying this to data. And as a proof of concept, we have applied this to about 10,000 light curves from the Galactic study that I mentioned. And we have found 23 new black hole candidates. By strong candidates, I mean that we didn't want to be rigid in a galactic model, so we tried 3 different initial final mass relations. So those are basically our prescriptions for how neutron stars and black holes form. And our strong candidates are those that are classified as black holes, regardless of which simulation we included as input. And all of those classifications for all 10,000 events, for all IFMRs, initial final mass relations, will be made public in a catalog accompanying this paper. And we, of course, couldn't do astrometric follow-up on those events because they are long gone. What we could do is we did a bunch of extra analysis, like their expected astrometric signal, their Gaia detectability, and so on. And in particular, one thing I would like to show is that we also verified it with an alternative method. So this is dark lens code that is developed by the team in Warsaw, led by Łukasz Wyrzykowski. And this is just another method of classifying dark lenses. And it's very different from ours in that it relies on dynamical information. So it focuses on motions of the lens and source in the galaxy. So all of our lenses here are classified as dark lens probability over 97%. It's usually around 99%. So they are dark and they also have masses of tens of solar masses. So they are black holes. We have some differences in estimating the astrometric signal. And those, as I said, can be very easily explained by those methodological differences and then relying on the dynamical information. But in general, we agree that those are all black holes. So that is just an independent check of our method. So now, drumroll, we would like to see how our method works on the only isolated stellar mass black hole discovered so far. And surprisingly, it gets classified as a white dwarf, considering only photometry. So now I have the difficult task of telling you that I do not mean to say it is not a black hole, because astrometric follow clearly determines it is a black hole. But I'm also not going to say that our classifier is useless and lies. So what you can see here is that this event falls into this very dense region of parameter space where probability contours are very crowded. So a little shift in parameters makes you move from white dwarf to black hole classification. And in fact, if you look at the reanalysis of all the events followed up in this observing program done by Lam and Liu, you can see that this event and the company, as I said here, are all more consistent from photometry alone with white dwarfs than black holes. So following the map was a high-risk decision that ultimately really paid off. Future black hole searches that focus on the lower regions, so that focus on here, are underway. We would have had a talk by Macy that would explain more about this, but unfortunately, we can't have it today, but there are ongoing programs following up events in this region of parameter space. We now have way more events, way more precise measurements, way more precise modeling, so we can really pick and choose those that are optimal to be black holes. And the last point here is that yes, it is an outlier, but is it an outlier from the real black hole population or just from our simulated population? Is our simulated population offset from the real one? So we can't really do statistics on a sample of one. But the idea is if we maintain this close link between our classifier and simulations and observations, we can refine our models. We can, for example, decide which initial final mass relation of the alternatives options existing in literature is right or closest to the truth. And we can both refine our chances for getting black holes and also refine our models of the galaxy. So this is something that really needs to be collaborative. Lastly, we have made this into a software package. So slightly it's fast. It has a primary application for microlensing that you can put really any science case you have or any set of microlensing parameters. All that you need is parameter values for samples that are labeled, where you say what class is the real class. And it's publicly available. We welcome contributions. We are very happy to, for example, welcome your own galactic simulation as one of the options. So these ones we use here are dedicated to mimic Ogle because our science case is classifying Ogle events, but we are happy to have any simulation integrated into this software. And we have submitted it to JOS. It is currently in review. So just to summarize my talk, we have created a classifier for microlensing events, and we have tested that it works for detecting black hole candidates. It is lightweight, flexible, and it is ideal to apply as initial filters. So as you can see in this picture, is something that picks out a needle, so black hole candidates in a haystack of stellar events. And as proof of concept, we picked 23 candidates for those black hole needles out of 10,000 archival Ogle events. And in the future, applying this method can help optimize astrometric follow-up and also verify galactic. This is a slide with all the papers if you would like to have a look. And last but not least, I would like to very warmly invite you to Heidelberg. Should the community like to choose this option, we are very happy to, and we have the capacity to host the next microlensing conference at this beautiful University of Heidelberg. So thank you very much for your attention. I can't go back. I can only go forwards.
Admire in the Zoom edit. On the left hand, there is a little X.
Thank you so much.
The buttons are not. Okay. I will ask you questions. So you mentioned that you did some simulations to check the prospects for the astrometry for these events. Could you talk more about this?
Of course. First filter we had to have was whether the timeline agrees with Gaia, and because it's 2002 to 2017, that was the main filter out. I think we had about seven. We had 7 black hole candidates that passed it, and then we had 4 that had, I think, no significant blending, which we did as filter. So there is possibility of the signal. We made a little prediction of astrometric signal we expect, but our error bars are large. So maybe there would be one event that would be observable in Gaia data. We can't tell for sure just because the uncertainties are this large. Ultimately, it seems that they will be too faint in Gaia. So either too faint or the time is not aligning. But just to see what could happen if we applied it to more recent events, which we can do in the future, hopefully, for other surveys. We took our events that, I will maybe go back to, I'll go back to the slide where I had all of our candidates presented. Perfect, okay, and you can see that there is this one that is expected to have high astrometric signal, and we made also a simulation of how it would look in Gaia data, and that's a figure in the paper you'd like to see, and that would have quite a big possibility to be visible in Gaia as a fit that's not consistent with 5 parameters.